Let's now move on to loops. Loops help us to repeat the same process or to execute the same statements repeatedly. MATLAB provides two options for looping. One is for loop and other one is while loop. The difference between the two is their nature. For loop repeats the commands for a fixed number of times, whereas while loop will keep on repeating until the condition becomes false. We will later see that we can sometimes avoid loops and increase the computational speed by vectorizing our code. That we will see later. Let's take an example for loop. So let's visit our good old distance code. Let's say I want to find the distance between the 2 points again, but this time the x0 coordinate is varying 10 times. Instead of calling the function 10 times, let's see how we can automate the process and we can use for loop for that. First we will describe the code. Let's clear the workspace command window and let's say x0 is 1 to 10, y0 is 2, x1 is 3.5 let's say, and y1 is 5. So now we have to run our for loop 10 times since there are 10 elements in this vector. So we have to find the distance between the 2 points as x0 moves 10 times. So we will write start for loop with for, then we will set our iteration variable or loop counter as we call it. I will start from 1 up to length of x0. Here again we have used the colon operator as you have observed. Also need not necessary the increment should be 1, you can even put 2, but in this case due to requirement we will write 1 colon length x0. Now for each iteration we will store the distance in vector r. So r of I will store that number in ith position in each iteration. So for first iteration the solution will be stored in first element of r, in the second iteration it will be stored in the second element and so on. So ri will be square root of x0 minus x0 of I. We have to extract ith element of x0 minus x1 square plus y0 minus y1 square. And we will tell MATLAB for loop has ended with keyword end. So let's save the program. Now let's run it. Since we have saved our program in a separate folder, but the current work directory is not that folder, so MATLAB is asking us to change the current directory to the folder where the program is saved. So if we say change folder, MATLAB will automatically do it for us. And as you can see, MATLAB has calculated R, and this is how the distance between the 2 points will vary, as x0 will change from 1 to 10. There is one more thing which we can do. We can calculate R in one more way by using the function dist between points. So let's say it's I, and here we will write, so we will say x0 is x0 of I, y0, x1 and y1. So let's compute both and we will compare it later. So let's run the program and let's see R and Y. So as you can see, either we can use this function to calculate the distance, or we can directly use the distance formula. We can use if-else statements in loops too. So let's see an example where we can use if-else statements in the for loop. The script will return number of positive elements, number of negative elements and zeros in the vector v. Here we have defined our vector v and initialized scalars p, n and z. So p will store number of positive elements in v, n will store the negative elements and z will store the number of zeros. So we will run our loop for length of v number of times so that all the elements in v are covered. Then we will use if statement to see whether the ith element in v is greater than 0 or is it less than 0, and the third possibility remains, is it equal to 0. So what happens if, let's say, in first iteration when I is 1, so v of 1 is 1, so MATLAB will check, is v of 1 greater than 0? Yes, so p will be updated to 1, so p will be p plus 1, and then it will exit the if else statement, go to end, again go to for loop. Then in the second iteration v of 2 will be minus 1, so MATLAB will check, is v of 2 greater than 0? No. So it will check, is v of 2 less than 0? Yes. So it will add 1 to n and again it will exit if, and it will go to end, and again the for loop continues until we reach the end of the vector v. Then finally we will print our result using printf command. So again it will tell us number of positive elements in v %d, because it will be an integer, and we have to mention p, n and z. So this is how the code will work. Let's see. So we will save it and let's run the code. So MATLAB has already printed the result that number of positive elements in v are 7, negative elements are 5, and there are 3 zeros. So let's count them. Let's count zeros first. There are 3 zeros. Yes. Let's count number of negative elements. Minus 1, 3, 5, 1, 2, 3, 4 and 5. So you see how it works. Similarly, you can combine if-else statements, switch statements with for loops and create some interesting loops. Similar to nested if-else statements, we can have nested for loops also. Let's take an example of nested for loop. So given a vector of length p, we will construct a matrix of size n cross m such that the product of n and m is p. That is, the number of elements in the matrices should be equal to number of elements in the vector which has length p. So here we have already written the program. So let's go through it. As usual, the first line is the description of the code. Then this p will define the length of the vector v, that is how many elements vector v will contain. Now see, for example, we have taken p to be 6, so the matrix size can be either 2 cross 3 or 3 cross 2. Now we will construct a random vector of integers. So for that, command in MATLAB is rand I, and then we have to give 3 inputs. So the first input is the range. Here I have written 2 times p. So the command rand I will create a vector of random integers between 1 and 2p. The next two numbers 1 and p will indicate the size of the vector or the matrix. So here, since we want a row vector, I have written 1 row and p columns. So Q will contain a matrix of random integers from 1 to 2p, and it will be of size 1 cross p. We will then initialize a variable k as 1. We will see how that is useful later. Now we will write the outer for loop. Outer for loop will begin from 1 to n, and then the inner for loop will begin from 1 and it will run for m number of times. And then we will say that p of I comma j is q of k, that is, in each iteration p of element in the ith row and jth column will be kth element in the vector q. Let's try to run this ourselves. So let's say for I equal to 1, we enter this for loop, outer for loop, then again we enter this inner for loop when j will start iteration. So j will be equal to 1. So in this line we have p of 1 comma 1 equal to q of k. If we don't initialize k, MATLAB will give us an error. So we have initialized k as 1. So in the first iteration we have p1 comma 1 is q of 1. After that k will add 1 to itself and become 2. So in the next iteration j will become 2 and we will have p of 1 comma 2 as q of 2. Again k will update itself to 3 and j will become 3, so p of 1 comma 3 will be q of 3. Now what happens, k will update itself to 4, but since m is only 3, so this inner for loop will run only 3 times. Since the counter has counted 3 times, we will exit this inner for loop and we will go to outer for loop. Now remember that k has value 4 and outer for loop will run for 2 times because the counter is set for 2. So outer for loop will run once again. Now the value of I will be 2. Again we will run this loop 3 times and k will update itself in each iteration. We will save this code and let's run it. So this is our vector q. It contains 6 elements and this is our matrix P. So as you can see, the elements in Q have been arranged in a rectangular matrix fashion. The size of Q is 1 cross 6 and the size of P is 2 cross 3. Similarly, if we want a matrix of size 3 cross 2, we just have to change N and M, and now you can check P is of size 3 cross 2. So this is Q and P. Now we come to while loop. As we have seen, while loop repeats the action as long as the condition is true. In other words, we can use while loop when we don't know how many times we have to repeat the action. That is when the count is unknown. So let's see an example of while loop. So if you are as careless as I, and if you define n to be 1 and you set condition on while loop that perform this action as long as n is less than 2, which is always true. So MATLAB will get stuck here and it will print this string forever. So as you can see, MATLAB has terminated the operation when we press Ctrl C. So in this way we can get out of an infinite loop. The smarter way would be not to get stuck in an infinite loop. So when using while loop, care must be taken that we should not use such conditions due to which we may get stuck into an infinite loop. We can also use break keyword to terminate such infinite loops after a particular range. Suppose I want to run this, let's say we will even print the number of times it is running. So %d and it will be m. Let's initialize m. M is 1 and we will increment m by 1 in each iteration. Then we will set a condition that when m will cross 50, break from the loop, come out of the loop. So let's save and let's go to command window. So as you can see here, MATLAB has printed this 50 times, then m will increment itself to 51, then MATLAB will check this condition, is m greater than 50? Yes, so it will break the loop and it will come out. Now let's see what vectorization means. If you see all our previous examples, you will notice that we are working with one number at a time, which essentially means that we are working with scalars. Take a look at this example. We accessed one element from the x0 vector in each iteration. That is, we used scalar as a variable, and to automate the process we used for loop. By vectorizing, we can use the entire vector as a variable. Vectorizing has its benefits. We replace many for loops and if else statements if we can vectorize our code. So this results in shorter codes, which increases readability of our codes, and debugging becomes quite easy. Let us solve the same example by vectorizing. Now you will ask what actually means vectorization. Well, we already know it. Vectorization basically means using array operations whenever we can. Let's see the same example, distance between the points, now using vectorization. As usual, the first line is information. So let's define x naught. It varies from 1 to 7. Y naught is 2. X1 is 3.5 and y1 is 5. We will store our result in R variable. It will be square root of. Now we will directly write x naught. We will treat x naught as a variable, though it is a vector. X naught minus x1. Since we are dealing with array and want to square each element in that vector x naught, we have to use array operation, and we will use a dot here to tell MATLAB to perform element wise operation. Plus y naught minus y1. So now let's copy this for loop from here so that we can verify that our R what we have written is actually correct. So y will store the distance between the same points, but it will be using the function dist between. So let's save our file and let's run it. Now let's go to command window and let's print R and Y. So as you can see, R computes exactly the same values as Y. It means that R has correct values. So if you observe here, we have replaced the entire function of for loop by just one line, and we have achieved that using array operations, which means we have vectorized our code. So whenever possible, try to vectorize your code. It will not only increase the computational speed, but the code will also look nice and it will be easy for the user to read it and understand it.
Finally, we come to animation. Here we will need most of those topics which we studied earlier. So why do we need animation? Animation helps in understanding the concepts better. Since it is a visual medium, it sticks in our brain for a longer time. Animation also makes complicated ideas easier to grasp. Many times while looking at a complex mathematical expression, we wonder, what does this look like physically? For example, here is expression for motion of particles in the acoustic domain due to a flexural wave in a structure. Don't worry, you will learn about this later in the course. So what does this equation convey? It tells us how particles will move in acoustic space if there is a wave in the structure. Tough to imagine, right? Let's see an animation of the same. So this black line indicates the flexural wave which is, let's say, set up in a beam, and due to this forward moving flexural wave, the acoustic particles in this domain have this type of motion. So instead of just looking at this equation and trying to imagine what it looks like, it would be much nicer if we can actually plot this and animate this in MATLAB. So how do we create an animation? Animation is an illusion created by showing a series of frames in rapid succession. Suppose I want to animate a chicken crossing a road. I will take snapshots at different times, then display them rapidly one after the other so as to create an illusion of motion. We use the same technique in MATLAB, but instead of taking snapshots in a camera, we use plot command. This can be considered as a guide to construct animations in MATLAB. The figure shows essential elements required for it. First, we define the variable that we need. Then we need a for loop to ensure that the animation runs for the specified duration of time. We then calculate the time varying quantities in each iteration of for loop. For example, while animating this, the time varying quantities were the displacement of particles. Then we plot our variables of interest. If we had to use a hold on, then don't forget the clear figure command, which is in MATLAB specified by a CLF. In animation, hold on and CLF go hand in hand. Now if we miss this draw now or pause command, we won't be able to see the animation because MATLAB will finish the computations too fast. So we need to use draw now to refresh the figure data. We can even use pause, where in the parenthesis we have to mention the number of seconds MATLAB will pause before giving the control to the next line. We repeat this over length of time vector. Finally, we can save this animation as a GIF or GIF file, show to others and impress them. So let's see two examples of animation in MATLAB. First, we will animate a simple pendulum. So here is the code for a simple pendulum. So here in this part we have defined our variables. For example, the length of string, acceleration due to gravity, initial displacement of our simple pendulum. I agree 45 degrees is too much, but in order to visualize the animation properly, let's use 45 degrees. Here we convert the initial displacement, which is in degrees, to radians. Then here we discretize the time variable and it runs for 2 cycles. And here are the Cartesian coordinates which we will use for plotting. Also these are the time varying quantities, as the displacement of the bob will change with time. Now here comes our for loop. So first we set the counter I from 1 to length of t. Then we write CLF since we are using a hold on. So if we miss this CLF but use hold on, all the figures will be printed on each other and it will be a complete mess. So hold on and clear figure go hand in hand. We then calculate the position of bob in terms of theta. So let's see the geometry of the simple pendulum. So here is our simple pendulum, and theta is measured from the vertical axis. The length of the string is L. The mass of the bob does not matter. And now we will plot our vectors in Cartesian frame. So we need x and y component of the displacement. But as you observed here, we are computing displacement in terms of theta. That is, I am calculating what this theta will be as a function of time, but I need y and x as function of time. So here we set up Cartesian coordinate system at this point where theta is 0, and then if we magnify this here, we see that this length is actually L minus L cos theta. So this much length is L into 1 minus cos theta, and this length is L sin theta. Therefore we will calculate theta as a function of time, and then we will use that theta to compute y and x. So here we do that. Here we calculate theta, which is solution for simple pendulum. Then we convert our theta into Cartesian coordinates x and y. Then we plot the bob. We plot the motion of the bob. This x and y are the coordinates of the bob as it moves in time, and we use a marker as a bob. Then we plot the string. Since the bob is moving and the string is attached to it, the string also has to move along with the bob. So we use line command for it. We could have used plot also, but line will also do. So the syntax for line is we have to mention two vectors. As you can see here, this is one vector, this is another vector, and this will contain x0, y0, x1, y1. So one vector will be for x coordinates, one vector will be for y coordinates. Then we plot the vertical line corresponding to theta equal to 0, and here we will print the theta values as our time progresses. To display that values, we use annotation text. So syntax for text is we have to mention the x coordinate, the y coordinate, and the string. Then we set some axis properties, and we can either use draw now or pause. So let's see our animation. So as you can see, this text will print this theta over here. One thing observe here that while using sprintf, we have used a double backslash theta. So it should be kept in mind that if we are using sprintf to print the Greek letters or the Greek symbols, we have to use a double backslash. A single backslash won't work, but while using printf or in titles and all, we can use a single backslash theta like that. Now if we want to see the path which is traced by this bob as it moves in time, so how do we do it? Observe here that x and y are vectors. So at each iteration, x is storing the x coordinates of the bob and y is storing the y coordinates of the bob. So we just have to plot x and y. Instead of x of I and y of I, if we plot x and y, we can trace the path of the bob. So let's plot it. Color is blue and marker is a simple dot. Let's call this as P0. P0 is the handle of plot for the path. So we will set P0 dot marker size to be 4. Now let's run this code and see whether we can see our path. So what happened, why we couldn't see? We used plot command, everything is right, MATLAB did not give any errors, so still why we could not see our path? The reason is we placed hold on here instead of here. So what happened, MATLAB plotted P naught, then since there was no hold on and we again asked MATLAB to plot P, it replaced P naught and it happened in each iteration. So we now rectify our mistake by putting hold on after P naught, and now let's see if we get our path. As you can see, here is our path. Now let's see how we can save our animation as a GIF file. So first we will define our file name. And then we write the following code. So this saving as a GIF file involves 2-3 processes. First, this get frame will capture the current axis as a movie frame. So what happens when we plot all this, we will generate a plot. So this get frame will grab that plot and save it as a frame, as a movie frame. Next step, we convert that frame to an image using frame to im function. This frame to im will return the image data associated with the movie frame. After that, we will convert the RGB image to an indexed image, and finally we will write that image to a graphics file using imwrite command. So these are the steps involved in converting the frame into image, and finally we will use for loop and this if else statement and imwrite to save the file as a GIF. Now let's save and run our code and see if our GIF is created. The file will be saved in the current work directory. Let's see. So as you can see, we have successfully saved a GIF. The next example which we will see is of a wave propagation. So there is a triangular pulse which will move forward with time. So let's first see the problem. So this is how our pulse will look like, a triangular pulse. So first what we will do is we will write a function to plot this pulse. So we will ask 3 inputs from the user. We will ask user the domain of the pulse, as you can see it is enclosed in the square brackets. Then we will ask user where the pulse starts. So we will ask user start. We will ask what is the width of the triangle or width of the pulse. We will ask user the domain, start and the width. The pulse will always be normalized, so that whatever start or width or range the user gives, the height of the pulse will always be unity. So let's see a function for that. So this is the function. So this is the function which will plot our pulse. So This is the definition line. 3 inputs are expected: the start, the width and the range, and we have one output parameter y. This is the help available for the function. So let's try one thing. Let's search our own function which we have written here. Help plot try. And as you can see, MATLAB will print exactly those lines which we mention here. So for other users to understand your function, how to use it and all, always mention the purpose and how to use it. So once the user has passed 3 values, we will store the range in variable x, we will store the start in variable v, and we will store the coordinate of width in w. So what I mean exactly is this: even though the width is this, we need this coordinate. So what we will do is, we know the start coordinate, we will add width to it to get the width coordinate. So that's why here we added start coordinate to the width. Now we will use the for loop in order to generate data in this range. So we will run for loop for the length of this discretized x. We will discretize our domain into small intervals, and then we will run the for loop over the length of this vector. So essentially the user must give range as a vector. Then we come to the if else statement. So why do we need if else is that there is condition for plotting. Before this start coordinate, the y values should be 0, and after this width coordinate, the y values should be 0, and in between this start coordinate and width coordinate, y of x will be a straight line. So we achieve that using an if else statement. So in this if statement, we check condition whether our x of I in the ith iteration is it greater than v and less than w, that is it lying within this range. If it is, then we calculate y using this formula. If it lies outside this range, then we set y of I to be 0. Finally we plot x and y. So let's try. So here how we will do it: n is the sampling frequency, that is we have sampled x into these many samples. The range we have given is -1 to 10. So the pulse domain will be -1 to 10. The pulse will start at coordinate 1 and the pulse width will be 3. So what we expect if we run this code is that the domain of the pulse will be -1 to 10. The pulse will start from 1 and the pulse will end at 4, since the width of the pulse is 3. So let's see. So as you can see here, the domain of the pulse is -1 to 10. It starts at 1 and ends at 4. Now let's play around. Let's say starting to 2 and let's say width to 3.5. Now let's run the code again, and again the start is at 2 and the end is at 5.5, so that the width of the pulse is 3.5, and observe that the height is always 1. So the height is always 1. This time the width is 2. So this is our function which plots the triangular pulse. Now let's come to the animation part. So here again x is the a domain. Observe that we used linspace command here to discretize x, and here we have used colon operator, and the start of the pulse is at 0. The width of the pulse is 1.5, let's make it 2, and we want our simulation to run for 9 seconds with increment of 0.1 second. Now we plot our forward moving wave here. Since we are plotting here, let's comment the plot command in the function. Let's save the function. Let's come back to the code. So here we store the output of this function. We have output parameter here, so we store the output of this function into y, which is basically information about the pulse, and x minus ti will ensure that the pulse is moving forward in time. Then we plot the function y versus x. Here y is the time varying quantity. Then we get the current axis handle in x. For animation purpose, don't forget to set the axis, because if you don't set axis in each iteration, MATLAB will adjust on its own and the animation will look like a complete mess. So one previous thing which we learnt was to use hold on and clear figure hand in hand. The second thing to keep in mind is always provide axis limits. First let us comment this and see how the animation is, so that we can appreciate it later. Okay, the decoration is off. So we have set the axis limits. We have labeled the x-axis, we have labeled the title, and we have placed a text which tells the domain and the time. So let's run the code. As you can see, the code has run for 9 seconds. It has told me what is the domain of my pulse, and it has also told me what is the width of my pulse. So as you can see, we have some ticks here. We are only interested in the x ticks, so that we can know what the domain of my pulse is. We don't want to see these y ticks. We are sure that each time the pulse is normalized, so amplitude will be 1. So how do we set this off? For that we use this command y tick off. Control T is the shortcut to uncomment, Control R to comment. Then we set the font name and font sizes for uniformity. Now let's run the code again. Observe the y-axis this time. As you can see, the y-axis labels are not visible, and the x-axis labels have changed the font, and the figure in all looks quite uniform. So we have seen two examples of animation. We have seen how to save animation as a GIF. We know what are the important factors that should be considered while doing an animation in MATLAB. Keep that guideline in mind when you do the coding. Don't forget simple things like axis limits, clear figure, hold on. So those are simple things and we tend to miss them, and then it will screw up the entire animation. So we have seen two examples of animation. The structure will be the same, only things changing will be the expression which you will use to calculate the time varying quantities. Rest everything, the structure will be same to save the files or for loop structure, etc. For practice, you can take few concepts from vibration or engineering mechanics and try to code them and create animations. For example, this animation will show that the x component of the velocity during the projectile motion will remain same, whereas the y component will change over time. So here you can see the y component is going down, down and down, so that finally it will go to 0 and then the gravity will pull it downwards and the velocity again starts increasing. So for this arrows I have used fewer plots. You can check them in MATLAB help. Next, this is a 3D plot which has been plotted using command plot3. So it shows some curve and a particle is moving along it, whose projection can be seen as this red dot. This is example of a rolling motion. The point at which it touches ground has 0 velocity. That's what we can see. Finally, about this energy. So this animation shows the total energy of the body in a projectile motion over the time. So at each instant the kinetic energy and the potential energy sum will remain same, though they may vary individually, their sum will always remain same. Similarly, you can pick any concept from these two subjects and try to animate. Try to attempt all the MATLAB assignments that will be uploaded during the course. It will not only develop your coding skills, but it will also help in understanding what we are learning. The different types of waves which you will come across can be beautifully visualized using MATLAB animations. So we come to the end of tutorials. If you have any doubt, please ask the queries in the MATLAB category which has been created in the forum. We will try our best to resolve it. Thank you.